Hello, I am Professor Janelidze. I am the program leader for the Mathematical Sciences program in the Faculty of Science. What I want to tell you about in this short video is what makes mathematics, specifically pure mathematics, different from what you've seen at school. The purpose of this video is to give you some kind of indication as to the value of taking pure mathematics modules during your studies at Stellenbosch University within the Mathematical Sciences program, and also possibly to give you some direction as to whether or not you would like to end up majoring in pure mathematics. So the mathematics that you see at school is largely based on one particular aspect of mathematics, which is measurement. One of the first encounters with mathematics, at least in an explicit way, is of course with numbers. And numbers are a very good example of mathematical objects that are introduced in order to measure something in real life, whether it's a quantity of objects or length or area and so on. However, mathematics itself is not just about measurement. In fact, in some sense, it is applied mathematics that is about measurement. So, indeed, the measurement is a kind of space where pure mathematics and real life come together. And of course, in such a space, you see all sorts of interesting applications and useful applications, right, of mathematics. And then that's the task of applied mathematics, to develop these applications further. The other aspects of mathematics that I would like to point out in this short video include structure, reason, and a phenomenon. Already in the realm of measurement, you find reminiscence of these three aspects. For example, the numbers, they form a structure. Natural numbers, for example, you can order them by succession. That's part of a mathematical structure. You also are able to add two natural numbers to get a third natural number. Such a process is called an operation, and also one of the ingredients of mathematical structure, and so on. Also, reason comes in with measurement, because you do want your measurements to be accurate, and you then employ the skills of reasoning to verify whether the measurement would be accurate enough or not. And that, of course, is very useful in making predictions, which is one of the important aspects of measurement. We want to perhaps predict whether the spaceship that we will fly indeed will land on moon, or whether maybe it will fly off and go to infinity and beyond. Okay, so there is also very nice appearance of phenomenon in the world of measurement. One of the striking examples there is a function. So a function itself is not a number. And at school, the functions you encounter are functions that assign another number to a given number. For instance, the function sine x. You take an input value for x, and then you have an output value sine x. The function itself the mathematical notion of a function arises from observing this phenomenon that it's useful to relate numbers in a functional way, and then of course also observing that lots of real life phenomenon can then be modeled by such relationships, which we call functions. But in mathematics, function doesn't need to do anything. It doesn't have to do anything with measurement. It's an abstract concept that assigns elements of one set, elements of another set, and there are numerous examples of functions which are not functions of numbers at all. Lots of real-life phenomena have been identified as principally being function, and that kind of profile of it is what allows us to have some kind of control and mastery over it. A good example are electromagnetic waves. These are not really material objects. They are very mysterious things, and the best handle on them that we have is to see them as mathematical functions. All right, so while the structure, the reason, and the phenomenon, they all arise in this world of measurement, they are also their own independent worlds, and there is lots of mathematics that you find in these worlds that have very, very little to do with measurement. In fact, in the most advanced and abstract form of mathematics, the only measurement we do is to maybe count how many variables we have in an equation, or we might not even have an equation at all, and we just want to count the number of things just to compare the size of one formula with another, and so on and so forth. All right, so let me give you some indication as to the independence of these worlds from the world of measurement. I will give you one example of a mathematical structure. It's called a topological space. In a topological space, you've got points, just like in our intuitive understanding of space. And then certain points form certain sets of points, which are called open sets. And the intuition behind that is that if you were to take, for example, a sphere in the physical universe, and you wanted to consider the sphere without its boundary, all the inside of the sphere, but not the boundary of it. So that would be an example of an open set in the topological space of our intuitive understanding of the real world. So what you do in a topological space, you basically study these open sets, and then you also have a notion of a function between topological spaces, which you can define to be continuous using the notion of an open set. And this notion of a continuous function goes back to functions of numbers, where some of you might have seen what it means for a function of numbers to be continuous. And that turns out to be an example of a continuous function between topological spaces. And of course, the notion of a topological space originally arises from our attempt to model the universe, breaking away from the boundaries created by a numerical way of thinking about the universe. And it opens up a new field of mathematics, which is called topology. And in this field, sometimes you do end up studying spaces that look more like the physical universe we are in, and then you do end up measuring things there. But also there is a large part of topology which has nothing to do with measurement, and which studies abstract features of the open sets and the continuous functions and so on. Then let's say a few words about reason. So one of the fields of mathematics that arises in this world is called mathematical logic. And what mathematical logic does is to try to give you basically almost like rules according to which we logically reason. And these rules constitute what one usually calls a logical system. And the objects in this logical system are the objects you want to talk about in a given scientific framework. And then you can do various things with those objects. For example, you can form sentences about them, and then you can do various things with those sentences. For instance, you can write something like this. So alpha could be a sentence saying that it's a wonderful day today, and beta could be a sentence saying that the roads are dry. And then by combining them using this operation, which is similar to how we combine numbers using various operations like addition and multiplication and so on, we get a new sentence which says that if it is a wonderful day today, then the roads are going to be dry. So what we can do with this is make it a bit more complicated. For example, now that we can express this operation as kind of algebraic structure, we can now form iterations of it and consider things like this, which when we make it even more and more complicated, these things now hardly arise in real life language. However, things like this underpin mathematical reasoning and very advanced mathematical proofs, which we do need in mathematics, even in the world of measurement, where we want to make sure that our answers are correct. So by studying these types of constructions in mathematical proofs, we get to understand how mathematical proofs work and have a better mastery of it, and then maybe even come to the point of asking a computer to verify for us whether a certain proof is correct or not. So this field, as I just hinted now, has lots to do with computer science. There is a lot of quite a big overlap between computer science and logic, for instance. Okay, then when we come to the phenomenon aspect, I'm not going to say much about this one. It would require, it kind of builds on the previous. So to explain this, one would require to have much better understanding of what structure is and what reason is. But let me just say that the fundamental task of mathematics is to understand a certain phenomenon. So in some sense, mathematics is very much here. And measurement itself is one type of phenomenon, and reason is another phenomenon, and structure is another phenomenon, but there are also many other phenomena. And so what one does in this world of mathematics is one tries to formalize and come up with a mathematical system that's supposed to model and capture the essence of a certain phenomenon. And then it turns out that such a system would kind of break down into fundamental mathematical ingredients, which will fall into these three worlds. So this kind of builds on these three, and at the same time provides the essence of what mathematics is. I would like to show here how the different modules in pure mathematics can be mapped out on this diamond-shaped plane that we've been discussing. The first year mathematics modules, which are 114 and 144, kind of begin where the school mathematics leaves off. They deal with calculus and linear algebra that are very much built out from mathematics of measurement, but they do make this little step towards the structural and the reasoning direction you will see the need for proving statements more than you saw the same need for maybe similar topics at school, and you will also encounter some concepts and constructions that are more clearly separated and isolated from the application scenario, and then kind of gives you a glimpse of mathematical structure. We also have 154 in the first year. This is a module that incorporates a bit more of logic into the curriculum. It's actually a module that's designed for students who are interested in computer science as well as mathematics. It certainly goes a bit more in the reason direction, although there's some structural ingredient to it as well. This module is not a compulsory module. The other two are. And then we have, in the second year, we have 214, 244. They go very much in the direction of structure. They actually build on these modules here. There is more calculus here with some analysis emerging. Analysis is basically calculus with more reasoning for demonstrating mathematical statements. And also you will encounter here a notion of a vector space, for instance, which later on you will see gives rise to topological space. So these modules very much take you to the structure, although the structure is not yet so explicitly isolated from the applications. And that will happen in the third year. But before we go to the third year, let's also talk about 278, which is largely a module about studying the logical underpinnings of mathematics. And so this is very much on this reason extreme of this whole picture. It's also a skills module. It's actually called Foundations of Abstract Mathematics. It develops your reasoning and general mathematical skills. Then in the third year, you see how the middle kind of gets filled up here, and also we're kind of approaching the top part of pure mathematics, this phenomenon aspect. So we've got 344. It's a module in discrete mathematics that doesn't really need that much of second year actually, even if it's a requirement to have to take that module. In a way, it's kind of based on elementary things, but on the other hand, it lifts off a bit from this measurement plane, and you will see some new kinds of structure arising here, and also reasoning that would be a bit more thorough perhaps than what you would have seen in this layer here in the first year. We've got 324, that's module in complex analysis. It's all about complex numbers, so still a lot to do with measurement, but the structure is coming in here as well. There's a lot of structure that the complex numbers possess. And then we've got the real analysis module 365, which is very much focused on rigorous proofs of theorems and going into details of what constitutes the real numbers. Then we have 314, that's a module in algebra. So this could be seen kind of as a further development from linear algebra from the second year. And 325 is a module in topology, and we already talked a little bit about topological spaces. 378 is a module in foundations of abstract mathematics. It kind of follows up on 278, although 278 is not a prerequisite module for 378. 378 is still a skills development module. It's also possible to do a project there, and so on. Okay, and so this kind of reaches the limit of what undergraduate mathematics offers, and if you want to go further and closer to understanding deeply this phenomenon aspect of mathematics, then you'll end up studying mathematics at the postgraduate level. Now, in the mathematical sciences program, there are two ways to study pure mathematics as your main subject. One is by following the mathematics stream, and the other is by following the abstract mathematics stream. And now this is a very rough picture, but more or less the mathematics stream is all about taking you from measurement to structure, whereas the abstract mathematics stream is about taking you from here to reason. And so, for instance, if you are interested in applied mathematics along with pure mathematics, you might prefer this stream more. On the other hand, if you're interested in computer science along with pure mathematics, you might prefer this stream more, but also there are lots of mixes between the two. The modules 114 and 144 are compulsory in the abstract mathematics stream, as well as 214, 244, and 378 and 278. On the other hand, in the mathematics stream, 278 and 378 are not compulsory, but there are some modules in the third year that are. So these modules are compulsory in the mathematics stream. In the abstract mathematics stream, as far as the third year modules are concerned, so these are the compulsory modules, but on top of that, you can also choose, you have to choose among these third year modules, but your choices will depend on what you want your second major to be in. There are certain second majors that abstract mathematics stream provides for you that the mathematics stream does not provide, and also vice versa. One such example is genetics, for instance, which you can do within abstract mathematics stream, but you cannot do within the mathematics stream. If you want to really kind of do as much pure mathematics as possible, then in the third year you will find double majoring in mathematics, and then you will be doing all the third year modules, and hopefully you would have also done the first year one, but it's not a requirement. I mean this 154 specifically. But then it doesn't really matter whether you're doing mathematics stream or the abstract mathematics stream. The end result will be the same. Okay, so depending on whether you like structure more or logic or reasoning more, that could kind of determine in very vague terms whether you would want to follow the mathematics stream or the abstract mathematics stream. But as I said, in many cases it doesn't matter which one you follow. In many other cases, when it's dependent on your second major, it very much does matter which stream you follow. But do not worry too much about this, because even if you make a certain choice now, and you probably already have done so, in the second year and third year you can always switch streams as long as you have all the modules that the other stream might have required from you. Okay, so that's what I wanted to show you with this picture. All right, so this is all I wanted to say in this video. Remember the key rule: if you love mathematics, then you should certainly consider studying mathematics, and if you love mathematics very much, then you should certainly consider making mathematics as your main subject of study at university. Thanks for your attention, and welcome to Stellenbosch University, and all the good luck for your first year and for the years to come.